So here's where we are on our pathway to ultimately deriving the QG geopotential height tendency equation and QG omega equation. We're roughly about halfway through, and we've gotten to the point now where we've written down the QG vector momentum equation. To get from momentum to vorticity is going to involve taking the curl of the momentum equation, specifically just its vertical component, to get us to the vorticity equation. This is a little bit complex, but we're going to take it step by step through this process to get us to a form of the vorticity equation that we'll be able to work with here going forward. So we've derived the momentum equation, which is written down right here, and now we're going to find the vertical component of its curl. So mathematically, this is what we're doing, and we can express this as a determinant to figure out what this is going to be equivalent to on the right-hand side, and this is going to tell us what math we end up needing to work out here. So writing this down as a determinant here, we only need to worry about the k-hat part of it because that's the only part we're interested in. And so starting at k-hat and reading down into the right and cross determinant here, we're taking the partial derivative with respect to x of the geostrophic total derivative of the meridional geostrophic wind. And then starting at k-hat reading down into the left, we're taking the partial with respect to y of the total geostrophic derivative of the zonal geostrophic wind. And so before we can work out this math on the right-hand side, we have to figure out how to find these two terms in parentheses here. So these are the components broken down of the compacted total derivative that we have on the left-hand side of our momentum equation. So the first step will be to expand all of the terms. So the left-hand side term will break into a zonal and a meridional component. For the right-hand side terms, we'll work out these two cross products. The good news is the first term in each of these cross products only involves k-hat, and so we have two zeros in the first row in our determinants here each time, which is going to simplify the math here quite a bit. So for the first one, starting with I-hat, reading down into the right, we have 0 times 0. Reading down into the left and cross determinant, we have negative F naught times VAG. So we have minus a minus F naught VAG, or plus F naught VAG I-hat. For J-hat, reading down into the right, we have negative F naught times UAG. Down into the left, we have 0. So we have here minus F naught UAG J-hat. And then for the k-hat term, we have 0 down into the right, 0 down into the left. So there's no k-hat part at all. So that finishes off the first one. We move to the second determinant. Starting at I-hat, reading down into the right, we have 0 times 0. Reading down into the left, we have negative beta y times Vg. So we have minus a minus beta y Vg I-hat, which is plus beta y Vg I-hat. For J-hat, reading down into the right, we have negative beta y times UG. Down into the left, we have zeros. So we have minus beta y UG J-hat. And then for K-hat, once again, we have 0 reading down into the right. We have 0 reading down into the left. So we're done. Applying these two cross products gives us these four terms over here. The next step would be to collect the I-hat and J-hat components together. Putting all the I-hat components together gives us this result. Putting all the J-hat components together gives us this result. And these are the two terms that we were looking for before. So we have the total geostrophic derivative of the meridional geostrophic wind, which is these two terms. And we have the total derivative of geostrophic derivative of the zonal geostrophic wind, which is these two terms right here. So returning to the curl of the momentum equation, we have this as our result here on the right-hand side, and now we can write that out in an expanded form. We know we're going to be taking the partial with respect to x of these two terms, and we're going to be taking the partial with respect to y of these two terms. And this equivalency right here, this equation, is going to end up being our QG vorticity equation when we're all said and done with it. We're just going to have to do a lot of simplification of this to get it down to a form that's useful to us. And the way we're going to tackle that is, for the sake of ease, we're going to deal with the left and right-hand sides of the equation separately. And then once we've done that, we'll put them back together at the end to see what our result ends up being. So we'll deal with the left-hand side first, and we're going to simplify this in a three-step process. First, we're going to swap the order of differentiation in both terms. Second, we're going to factor out the common derivative that results. And thirdly, we're going to simplify the result. So we start with what we have in the blue box here, and the first step is to swap the order of differentiation. So in the first term, we're going to move the partial with respect to x inside the parentheses, and we're going to move the geostrophic total derivative outside. That's going to give us this. In the second term, we're going to do the same thing. We'll move the partial with respect to y inside, we'll move the total geostrophic derivative outside, and that's going to give us this. So we've swapped the order of differentiation. Next is to factor the common derivative. The common derivative appears to be the geostrophic total derivative. So we factor that out and we end up getting this. The third step is to simplify the result. So that involves simplifying the part here that's in parentheses. And so we ask, what does this appear to be? We have partial vg partial x minus partial ug partial y. Partial v partial x minus partial u partial y. Sounds like the vertical component of vorticity. And it is, and in this case more specifically, it's the vertical component of the geostrophic vorticity. And so the whole part in blue, in this blue box on the left-hand side, collapses down to this one single term. And it makes sense that we should get something involving vorticity because we were, after all, deriving the QG vorticity equation. So this is going to be the left-hand side, and we're finished with that now. We're going to write it out as this total derivative here. For the right-hand side, we're going to have to work the math out on these two terms. We have partial x of this stuff, and we have partial y of this stuff. And so as you look at the various things that we're going to have to take the derivative of here inside the parentheses, we have f naught. F naught's a constant, so that's good. We have UAG, which is going to be a variable. We have beta, and the question is beta going to be a variable or going to be a constant? So applying these derivatives, how do we deal with beta? And the good news is here we get to treat it as a constant, and that is thanks to the work that we did in deriving the QG momentum equation, where we invoked the beta plane approximation in our Taylor series that we worked out from before. So we have two constants inside the parentheses. F naught and beta are both constants. UAG, Y, and UG are variables. Similarly over here, VAG, Y, and VG are going to be variables in this second term. So now we can work out the derivatives knowing that. And for the first term here, we're applying the partial with respect to x to this term. The f naught part is constant, so negative f naught will stay out in front, and then we'll have the partial of UAG with respect to x. In our second term, we're going to need to apply the product rule here because we have two variables multiplied together, y and ug. So the first is y, the second is ug. So first times derivative of the second, we'll have negative beta y times partial x of ug. And then second times derivative of the first, so negative beta ug times partial y partial x. And when you think about partial y partial x, this is saying how does y change as x changes? If we're only moving in the x direction, then y doesn't change, and so partial y partial x is 0, and that means that this entire term is 0, so that's going to just drop out. And that finishes the first of the two terms inside the blue box. Then we move to the second term. In the first one here, we have f naught times VAG. F naught's a constant, so we're just going to get negative f naught times partial VAG partial y. In the second term, beta is a constant, and we have y times VG. The first is y, the second is VG. So first times derivative of the second is going to be negative beta y times partial VG partial y. And then second times derivative of the first is going to be negative beta VG times partial y partial y. Partial y is just unity, and so that final term will simplify just a bit. Okay, so that's what we've done so far. We've applied the derivatives and we've written all these terms out. Now we can simplify a little bit by collecting out some things that are common. And if you look on the right-hand side, there are two terms here that both involve negative f naught, those two. So we factor the negative f naught out of those and we get this. There are two terms on the right-hand side that involve negative beta y. We factor the negative beta y out and we get this. And then that just leaves the negative beta vg here left over on the end. So this is the result that we get having simplified what we've done so far. The next step will be to rewrite the terms in parentheses in vector form. If we look at the first term in parentheses here, we have partial UAG partial x plus partial VAG partial y, which sounds like the divergence of the total ageostrophic part of the wind. So negative F naught times the dot product of del dot VAG. And then the second term in parentheses, we have partial UG partial x plus partial VG partial y, which sounds like the divergence of the geostrophic part of the total wind. So we have minus beta y del dot VG, and then we also have on the negative beta VG here on the end. At this point, thanks to some things that we did a little bit earlier, we can take that whole second term of the three terms on the right-hand side and cross it out because, based on some earlier work, we are treating the geostrophic wind as being non-divergent. So the divergence of the geostrophic wind is 0, so this entire middle term drops away. And if we go back when we were working out the QG momentum equation and we were rewriting the geostrophic wind here, we rewrote it this way. So we rewrote, instead of using 1 over F naught plus beta y, k hat, we dropped off the beta y part here so that the geostrophic wind would be exactly non-divergent. Why did we do that? A big part of the reason was to help simplify the QG vorticity equation, which is exactly what we're working out now. And this is a great simplification step here, the ability to drop out that second term. And so that leaves us with just these two terms left over. At this point, we'll take this dot product here in parentheses, which is the divergence of the ageostrophic part of the wind, and we're going to rewrite that using the continuity equation. Specifically, we're going to use this form of the continuity equation. So any divergence or convergence of the ageostrophic wind is going to result in some type of vertical motion, partial omega, partial p, in our isobaric coordinate system. And these three terms added together should equal 0 if continuity is to be preserved. If we move the partial omega partial p term to the right-hand side, we get negative partial omega partial p equals these first two terms, and those first two terms are equivalent to this dot product. So we can replace this dot product here with just negative partial omega partial p from the continuity equation. And then these two negatives will cancel out, and so we end up with, on the right-hand side, two terms, F naught partial omega partial p minus beta Vg. And we're almost there. The last part of this is we don't want the total geostrophic derivative of the geostrophic vorticity. We just want the local tendency of the geostrophic vorticity. So we're going to break up this total derivative into its local tendency plus its advective parts here. We'll move the advective parts to the right-hand side of the equation. And the very last thing we need to do here is just some simplification on these terms on the right-hand side, and then we will be done and we'll have our QG vorticity equation. So this is what we have right now. We'll slightly rewrite this by rewriting beta as what beta really is, which is the change in planetary vorticity with respect to y. So we rewrite beta as partial f partial y. And we can start doing some simplification here on the right-hand side. First of all, we look at these first two terms. We have minus UG partial zeta g partial x minus VG partial zeta g partial y. UG and VG taken together are the total geostrophic wind. Partial zeta g partial x, partial zeta g partial y are the gradient of zeta g. And so we can rewrite this as this dot product. For the last term here, the minus partial f partial y VG, we can rewrite this also as a very similar looking dot product as the total geostrophic wind dotted with the gradient of planetary vorticity. To verify that that's okay, that we did that, we can work out this dot product. So VG expands into UGVG, and del F expands into partial F partial X, partial F partial Y. When we apply the dot product, we get for our first term negative UG partial F partial X. For our second term, negative VG partial F partial Y. And when we look at these two terms, recognize here that F, planetary vorticity, does not change in the x direction. It only changes in the y direction. So this whole first term, partial F partial x, is 0. And that whole first term drops out, leaving us with just minus VG partial F partial y, which is exactly what we started with up here. So rewriting this partial derivative as this dot product here is perfectly fine in doing this. And the reason that we do this is so that we can take this term and this one and combine them together to simplify things a bit. So this checks out okay. And now we put those two terms next to each other, these two dot products next to each other, and we have left over this F naught partial omega partial P term right here. And the very final thing we need to do to simplify this is to consider how can we combine those terms together. And here it is helpful to expand out and work out these dot products to see what falls out of this at the end. So in the first one here, we would have minus UG partial zeta G partial X minus VG partial zeta G partial Y. Then we'd have a minus UG partial F partial X and a minus VG partial F partial Y. So we end up with these four terms when we've applied these two dot products. Now we can factor out some commonalities. We have two terms that involve minus UG partial X, and we have two terms that involve minus VG partial Y. So we put those together and factor out, and what factors out each time, what's left over each time after the factoring is zeta G plus F, zeta G plus F. And so we have a partial X zeta G plus F, and we have a partial Y zeta G plus F, which sounds like the gradient of zeta G plus F. And so that leaves us with this as our result, negative VG, our geostrophic wind, dotted with the gradient of zeta G plus F. And so these two terms will combine into this single term. And that means that we now in our equation have this, and this is where we can stop. After all of that work, we have now written down the QG vorticity equation, a form of which that is going to be useful to us. We can also express this by rewriting the geostrophic vorticity. Instead of zeta G, we can express it as the Laplacian of the geopotential divided by F naught. And we're going to work that out a little bit later to show that equivalency. But that notation will be what we actually use when we go forward in our derivations and we write out the geopotential tendency and the omega equations. So we'll show why these two things are equivalent here in just a little bit. But for right now, this is where we wind up with our QG vorticity equation. So the next thing that we will do is we will talk about the physical interpretation of this. What do these two terms actually mean, and how can we assign some meaning to those? But for now, we can at least take some satisfaction in the fact that we have accomplished step 4. We have written down now the QG vorticity equation. And the next step will be to do a quick little interpretation of what we have, and then we will move on to the QG thermodynamic equation after that.